Welcome to Learn Electrical. In this video, we will discuss an introduction of high voltage DC generation. Various methods of high voltage DC generations will be discussed, like half wave rectification, full wave rectification, voltage doubler circuit, voltage multiplier circuit, and Cockcroft-Walton voltage multiplier circuit. Let's start from why high voltage DC is necessary. DC high voltage are applicable in pure as well as applied physics for research purpose also. It is also used in medical science. For example, in X-rays, high voltage DC are used. Similarly, high voltage DC are also used for electrostatic precipitation of ash in thermal power plant, in electrostatic painting, and in other various industrial applications. It is used. Similarly, in power system and power system apparatus, high voltage DC test is carried out as type test or routine test. For example, in high voltage AC cables, high voltage DC are used for testing. It is used to test the performance of high voltage AC cables. We will discuss about high voltage AC cable testing in testing chapter. And thus, for all these applications, high voltage DC is to be generated, and the most common method or the most common principle of high voltage DC generation is same as low voltage DC, that is rectification. This is produced from rectification, DC rectification process. For high voltage, power diodes are used for rectify instead of normal simple electronics diodes. Another method for high voltage DC generation is voltage doubler, or more to say voltage multiplier circuit. We are going to discuss about these topics in this video. You can see a laboratory setup for high voltage DC generation. You can see high voltage rectifiers, isolators, grounding switch, high voltage electrode, and smoothing capacitor, measuring resistors, earthing rod, and you can also see the aluminum plates that are laid on the ground that are for creating equipotential surface. And this is a general configuration of high voltage laboratory. Rectification and voltage doubler circuit. We all know rectification might be high half wave or full wave rectification. We will discuss about half wave and full wave rectification here, and we also discuss about voltage doubler type rectifier. We have to understand is the rectification may be electron tube or solid state devices. The solid state device means semiconductor devices. The more commonly preferred diodes for high voltage rectification are silicon diode, power electronics diodes. You can see a normal, a simple figure of a diode here, and its technical data or technical specification is here. You can see its various rating. Difference between normal electronics diode and power electronics diode is its size and weight. Normal electronics diode weighs less than 8 gram, but power electronics diodes are comparatively larger. You can see in the specification. Okay, let's discuss all of them serially. At first, half wave rectification. Half wave rectification itself, the word itself speaks what actually it is. The half portion of the wave here, AC waveform, is rectified to DC. In first figure, you can see a transformer. In this figure, you can see a transformer. It will transform low voltage, generally distribution voltage, to higher voltage level as up to 100 or 200 kilovolt, and the power diode or rectifier used will conduct when it is forward bias, and the capacitor here is used as a filter, and here the load, that is RL, might be any test object. During rectification, output of high voltage transformer is shown in second figure, that is the input sine wave for rectifier circuit. And the power diode will conduct for positive half cycle. In this period of time, the capacitor C is also charged up to maximum voltage, that is maximum value of input sine wave. In negative half cycle, the diode will be reverse biased. In negative half cycle, the diode will be reverse biased and capacitor is discharged into the load in that period, which can be understood better with this output waveform. While choosing the value of C, we should choose C such that the time constant C into RL is at least 10 times that of the period of the AC supply, and the rectifier value must have a peak inverse rating of at least 2 Vmax so that smoother DC can be generated. And similarly, to limit the charging current, an additional resistance R is provided in series with the secondary of the transformer. Here it is not shown, and generally the high voltage diodes are also made up of several kilo ohms of resistance, as we saw in previous slide. In its specification, you can see its inverse peak voltage rating, and also you can see its resistance 100 kilo ohm. Okay, now let's get into full wave rectifier. Our full wave rectifier will rectify the full wave, not only the half portion of the wave. In DC generation can also be made with full wave rectifier. Figure is shown here. A center tap transformer is shown, and two rectifiers A and B are used to rectify the input sine wave, and C is used as a capacitor, is used as a filter, and similarly RL is the load, or you can say it is a test object. If we are using that generated high voltage in testing, RL is a test object. For positive half cycle, rectifier A will conduct, and for negative half cycle, rectifier B will conduct and charges the capacitance or capacitor. Waveform here will clarify my statements. Here ripple will be less and smooth. DC can be generated, but with more costlier than half wave rectifier, as it has more components rather than not just one rectifier. It has two rectifiers. It will have more cost. Let's discuss on the ripple, what actually ripple is. Actually, ripple is the fluctuating AC component presented in rectified DC output. It is shown as del V in the waveform. Del V depends on supply frequency. The ripple voltage depends on supply frequency and time constant of C and RL, that is C into RL, and also on the reactance of the supply transformer. Ripple voltage for half wave is larger than that of full wave, and the frequency of ripple voltage for half wave is same as that of supply frequency, while for full wave the ripple frequency is twice than that of supply frequency. We can see these things from figure clearly, and in order to keep the ripple voltage low as much as possible, the filter capacitance should be properly chosen. We have to choose the filter capacitance C properly. Well, I have shown a comparison of half wave and full wave rectification process, the number of diodes, output DC, ripple frequency, ripple factor, peak inverse voltage of rectifier. I want to highlight you that the output voltage or average output DC voltage, that is less than the Vmax in both the case. Hence, if we need any higher value of output DC, high voltage DC, then the both methods are not suitable. So we are going to learn about the third process, its voltage doubler circuit or Greinarcher Voltage Doubler circuit. Both full wave and half wave rectifier circuit produce a DC voltage less than that of AC maximum voltage, but the voltage doubler circuit will produce the voltage that is double to that of the supply voltage. We can see a general circuit diagram of a voltage doubler circuit. Here is a high voltage transformer, two capacitors, two rectifier and a load. The voltage across the output, that is across the load, will be 2 times the supply voltage V. If V is the supply voltage, then the voltage across the load will be 2V. So it is known as voltage doubler circuit. In voltage doubler circuit, consider a negative half cycle. During negative half cycle, R1 is forward bias, so that C1 will be charged up to the voltage V through R1, and the polarity will be additive for next half cycle. I mean to say, in next half cycle, the voltage across the transformer will be V, and the voltage across the C1 will be also V, that are additive, so that the C2 will be charged to 2V through R2, and the voltage across C2 is appeared as load, that is 2V. By this way, a voltage doubler circuit doubles the voltage. Okay, you can see the waveform. The first one is the input voltage waveform, and this, the third one, is the DC output voltage waveform with capacitor filter. And this is how the voltage doubler circuit works. Now, voltage multiplier circuit. In voltage doubler circuit, we can make the output DC voltage double of the input supply voltage. In voltage multiplier circuit, we can increase the output DC voltage n times. It works on the similar principle than that of the voltage doubler circuit. We can see a number of capacitors and diodes are arranged as in figure. This figure, rectifiers and capacitor are arranged such that capacitor are charged at parallel from AC input supply. These voltages are added in series to get the higher value of DC output voltage. Number of voltage multiplier circuit can be connected in series if we require, or if you wish to get even more higher output voltage. In the top figure, you can see a two-stage voltage multiplier circuit. From this two-stage voltage multiplier circuit, we will going to learn how does the voltage multiplier circuit works. Here it is two-stage voltage multiplier circuit, and its output DC voltage will be 4 times the input voltage. Here Vi is the input voltage, then output voltage, this output voltage at terminal E will be 4 times this input voltage. Now let's understand how voltage multiplier circuit works and how it multiplies the voltage. At first, see, here are 4 numbers of diodes and 4 numbers of capacitors, D1, D2, D3, D4, similarly C1, C2, C3, C4, and I have labeled the points A, B, C, D, E and F respectively. At first, let's go from negative half cycle. During negative half cycle, D1 will conduct, thereby charging the capacitor C1 to Vi, that is supply voltage. The capacitor C1 will be charged to V1, so that the C1 will have higher polarity at B. At point B, C1 will have positive or higher polarity. This is charged, and it will have here positive, and this is negative, and will have a voltage Vi. Now, in next half cycle, or next positive half cycle, the voltage at VB will be 2Vi. At this point, the voltage will be 2Vi. It is because in positive half cycle, this supply voltage will have Vi, and this capacitor has Vi voltage. Hence, these two voltages are additive. are in series, so the voltage across PV will be 2 VI. Now at this instant D2 conducts, thus this C2 is charged with voltage of VV, that is 2 VI, and this D2 will conduct and it will charge C2 with voltage 2 VI. Now let's go to next half cycle, that is negative half cycle. Voltage at point C at next half cycle, this will be by previous half cycle, this will be 2 VI with this polarity. In negative half cycle means higher polarity at this side. The voltage at point C will be 3 VI. It is because this 2 V1 is additive with the source, hence PC is 3 VI. Also at that instant D3 will conduct, thus charges the C3, and this voltage will appear, and this conduction of D3 will appear certain voltage at D, so C3 will also be charged. When D3 conducts, this will charge C3 and C1, and the voltage at point D will charge C3 and C1 by 3 V1, so C3 will have 2 V1 voltage and C1 will have V1 voltage. Now in next positive half cycle, and this is V1, this voltage across C1 will also be V1, and voltage across C3 is 2 V1, and hence the voltage at point D will be the sum of V1, V1 and 2 V1, that is 4 V1. Hence the 4 V1 will be appeared at point E, that is output will be appeared as 4 V1. This voltage will charge the C4 by 2 V1. Hence the output voltage will be 4 times the input voltage. Thus we can say we can get higher output voltage than input supply voltage. This is two-stage multiplier circuit. We can get output DC voltage Vout, that is 4 times input voltage. The first capacitor C1 was charged up to Vi, that is input voltage, and all other capacitors are charged by 2 Vi. We can use the same principle to understand the 3-stage multiplier circuit. If it is 3-stage multiplier circuit, its output will be 6 times the input, and for n-stage multiplier circuit we can get output DC voltage Vout, that is equals to 2 into n times the input voltage. Hence voltage multiplier circuit multiplies the input voltage. Hence high voltage DC can be generated using voltage multiplier circuit. Okay, after voltage multiplier circuit, we will here discuss about Cockcroft-Walton voltage multiplier circuit. It is similar to voltage multiplier circuit. It is named as Cockcroft-Walton voltage multiplier circuit because it is named after British physicist John Cockcroft and his friend Ernest Thompson Walton. Cockcroft-Walton generator or multiplier is an electrical circuit that generates high DC voltage from low value of AC or pulsating DC. You can see in the figure this combination C1, C2, D1 and D2 is similar to voltage doubler circuit, which we had already discussed. And as we previously discussed voltage multiplier circuit, this remaining part is voltage multiplier circuit. For higher output voltage, that is 4 times, 6 times or 2n times of the input voltage, the circuit is repeated in cascade as shown in figure. Here each capacitors C2, C3, C4, C2n are charged up to 2 Vmax, and C1 is charged up to V1 or Vmax, as we already discussed in previous voltage multiplier circuit discussion. Here these diodes D1, D3, D5, D2 n minus 1 will conduct on negative half cycle, while D2, D4, D2n's will conduct on positive half cycle. And this is the AC transformer. During negative half cycle, this D1 will conduct and charge the C1 up to V input voltage, and during positive half cycle, this C2 will be charged to 2 V input voltage through D2, and by this way, as similar to voltage multiplier circuit, Cockcroft-Walton voltage multiplier circuit also works. At last, the high voltage DC is generated across the load in between this point and this point. Okay, in this figure you can see the ripple voltage and the voltage drop in cascade voltage multiplier circuit. Del V is the ripple voltage, and this is the input voltage waveform, and this is the output voltage waveform. This is 2n times the Vmax, or 2n times the input voltage. This can be shown in this graph. For Cockcroft-Walton voltage multiplier circuit, we can derive the total ripple values, that would be equals to I into 2n times 2n plus 1 by 2fc, and similarly voltage drop would be as mentioned in this equation. If you wish to see the derivation, you can see the reference books if necessary. For numerical, these values might be helpful for you to solve the numerical questions related to n-stage Cockcroft-Walton voltage multiplier circuit. We have to use this formula. If you wish to see the detailed derivation, please refer the reference book that I will show you at last. And the voltage regulation would be voltage drop divided by 2n into Vmax into 100. Similarly, in these types of numerical problem, you might be asked to find the optimal number of stages. For this, you can use this formula. This is applicable for number of stages that is equals to or greater than 5. Similarly, maximum output voltage for that optimal number of stages is given by this formula, where n is the number of stage of the multiplier, and I is the load current for rectifier, and f is the supply frequency. Here I have included a cascaded rectifier unit with pulse generator. The working is quite similar to the voltage multiplier circuit. Here you can see a pulse generator and a DC supply and another bias voltage. The pulse generator will generate a pulse, and this whole circuit can be used to generate the high voltage DC using a DC power supply of about 500 volt. With this pulse generator, it is sufficient to generate a high voltage DC of about 100 kilovolt with suitable number of stages, and the pulse frequency should be at about 500 to 1000 Hz, and at this case the ripples are also quite low, that is nearly less than 1%. Hence, in this video I discuss the methods of high voltage DC generation, that is rectifications, and that is half wave rectification, full wave rectification, voltage doubler, and voltage multiplier circuit. This is all about DC high voltage generation. Now I have listed the reference books for more explanations, and for the derivation that I have not mentioned in this video, you can see on this reference book. Okay, keep watching Learn Electrical. Thank you.